Hi everyone. Let's talk about the Bohr model of the hydrogen atom. To give some background, J.J. Thomson's plum pudding model tried to describe the atom, but Ernest Rutherford later found it to be incorrect, so he created his own version called the Rutherford model. However, Rutherford's model did not align with the new discoveries found in quantum mechanics, so Danish physicist Niels Bohr set out to create a new model of the atom. In his model, the electrons orbiting the nucleus were in discrete stable energy levels, inspired by the discovery of quantization of energy. So, let's talk about Bohr's model for the hydrogen atom. The electron orbiting the nucleus can take up discrete energy levels, with the energy of each level calculated by the negative Rydberg constant divided by the energy level squared. So, for the first energy level, it's negative 13.6 electron volts, then the second level is negative 3.4 electron volts, and so on. The electron can change energy levels by absorbing photons with specific energies. To illustrate this process, imagine this scenario where the electron is just chilling in its first energy level, and a photon with the right amount of energy collides with a hydrogen atom. The electron absorbs the photon, causing it to jump up in energy levels. In this case, it jumps up to the second energy level. However, the opposite effect is also true, where an electron will jump down to a lower energy level and emit a photon. As per the law of conservation of energy, the photon must have energy equal to the change in energy of the electron. So going back to the equations for energy levels, the difference in energy is the final energy level of the electron minus the starting energy level. Or, this simplifies to the difference in energy is the negative Rydberg constant multiplied by 1 divided by the final energy level squared minus 1 divided by the initial energy level squared. And since the photon is, well, a photon, we know its energy is equal to the Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. For hydrogen, the different energy transitions are labeled as different series, called the emission spectrum. So when transitioning down to the first energy level, it's the Lyman series, and then when transitioning to the second energy level, it's the Balmer series, and so on. Now going back to the equations for the photon's energy and energy levels, we can calculate the wavelength of the photon that's emitted. The Balmer series of hydrogen is where the electron transitions down to the second energy level, and it has 4 spectral lines that are in the visible light wavelength. The first transition line is called the H alpha line and is red. The second spectral line is a light blue line called the H beta line, while the third line is a darker blue called the H gamma line, and the fourth visible line is the purple line called the H delta line. These emission lines have many uses, such as in astrophysics, where these emission lines, particularly the H alpha line, are very crucial for detecting hydrogen.